This video introduces the learning algorithm for a linear neuron. This is quite like the learning algorithm for a perceptron, but it achieves something different. In a perceptron, what's happening is the weights are always getting closer to a good set of weights. In a linear neuron, the outputs are always getting closer to the target outputs. The perceptron convergence procedure works by ensuring that when we change the weights, we get closer to a good set of weights. That type of guarantee cannot be extended to more complex networks, because in more complex networks, when you average two good sets of weights, you might get a bad set of weights. So for multi-layer neural networks, we don't use the perceptron learning procedure, and to prove that when they're learning, something is improving, we don't use the same kind of proof at all. They should never have been called multi-layer perceptrons. It's partly my fault, and I'm sorry. For multi-layer nets, we're going to need a different way to show that the learning procedure makes progress. Instead of showing that the weights get closer to a good set of weights, we're going to show that the actual output values get closer to the target output values. This can be true even for non-convex problems in which averaging the weights of two good solutions does not give you a good solution. It's not true for perceptron learning. In perceptron learning, the outputs as a whole can get further away from the target outputs, even though the weights are getting closer to good sets of weights. The simplest example of learning in which you're making the outputs get closer to the target outputs is learning in a linear neuron with a squared error measure. Linear neurons, which are also called linear filters in electrical engineering, have a real valued output that's simply the weighted sum of their inputs. So the output y, which is the neuron's estimate of the target value, is a sum over all their inputs I of a weight vector times an input vector. So we can write it in summation form, or we can write it in vector notation. The aim of the learning is to minimize the error summed over all training cases. We need a measure of that error, and to keep life simple, we use the squared difference between the target output and the actual output. So one question is, why don't we just solve it analytically? It's straightforward to write down a set of equations, with one equation per training case, and to solve for the best set of weights. That's the standard engineering approach, and so why don't we use it? The first answer, and the scientific answer, is we'd like to understand what real neurons might be doing, and they're probably not solving a set of equations symbolically. An engineering answer is that we want a method that we can then generalize to multi-layer nonlinear networks. The analytic solution relies on it being linear and having a squared error measure. An iterative method, which we're going to see next, is usually less efficient, but much easier to generalize to more complex systems. So I'm now going to go through a toy example that illustrates an iterative method for finding the weights of a linear neuron. Suppose that every day you get lunch at a cafeteria, and your diet consists entirely of fish, chips and ketchup. Each day you order several portions of each, but on different days it's different numbers of portions. The cashier only tells you the total price of the meal, but after a few days you ought to be able to figure out what the price is for each portion of each kind of thing. In the iterative approach, you start with random guesses for the prices of portions, and then you adjust these guesses so that you get a better fit to the prices that the cashier tells you. Those are the observed prices of whole meals. So each meal you get a price, and that gives you a linear constraint on the prices of the individual portions. It looks like this. The price of the whole meal is the number of portions of fish, X fish, times the cost of a portion of fish, W fish, and the same for chips and ketchup. So the prices of the portions are like the weights of a linear neuron, and we can think of the whole weight vector as being the price of a portion of fish, the price of a portion of chips, and the price of a portion of ketchup. We're going to start with guesses for these prices, and then we're going to adjust the guesses slightly so that we agree better with what the cashier says. So let's suppose that the true weights that the cashier is using to figure out the price are 150 for a portion of fish, 50 for a portion of chips, and 100 for a portion of ketchup. For the meal shown here, that will lead to a price of 850, so that's going to be our target value. Let's suppose that we start with guesses that each portion costs 50. So for the meal with 2 portions of fish, 5 of chips and 3 of ketchup, we're going to initially think that the price should be 500. That gives us a residual error of 350. The residual error is the difference between what the cashier says and what we think the price should be with our current weights. We're then going to use the delta rule for revising our prices of portions. We make the change in a weight, delta Wi, be equal to a learning rate, epsilon, times the number of portions of the ith thing, times the residual error, the difference between the target and our estimate. So if we make the learning rate be 1 over 35, so the math stays simple, then the learning rate times the residual error for this particular example is 10. And so our change in the weight for fish will be 2 times 10. We'll increase that weight by 20. Our change in the weight for chips will be 5 times 10. And our change in the weight for ketchup will be 3 times 10. That'll give us new weights of 70, 100 and 80. And notice the weight for chips actually got worse. There's no guarantee with this kind of learning that the individual weights will keep getting better. What's getting better is the difference between what the cashier says and our estimate. So now we're going to derive the delta rule. We start by defining the error measure, which is simply our squared residual summed over all training cases. That is the squared difference between the target and what the neural net predicts, or the linear neuron predicts, squared and summed over all training cases, and we put a half in front, which will cancel the 2 when we differentiate. We now differentiate that error measure with respect to one of the weights, Wi. To do that differentiation, we need to use the chain rule. The chain rule says that how the error changes as we change a weight will be how the output changes as we change the weight, times how the error changes as we change the output. The chain rule is easy to remember. You just cancel those 2 dy's, but you can only do that when there's no mathematicians looking. The reason the first one, dy by dw, is written with a curly d is because it's a partial derivative. That is, there's many different weights you can change to change the output, and here we're just considering the change to weight I. So dy by dwi is actually equal to xi, and that's because y is just wi times xi. And de by dy is just t minus y, because when we differentiate that t minus y squared and use the half to cancel the 2, we just get t minus y. So our learning rule is now we change the weights by an amount that's equal to the learning rate epsilon times the derivative of the error with respect to a weight, de by dwi, and with a minus sign in front because we want the error to go down. And that minus sign cancels the minus sign in the line above. And we get that the change in a weight is the sum over all training cases of the learning rate times the input value times the difference between the target and actual outputs. Now we can ask, how does this learning procedure, this delta rule, behave? Does it, for example, eventually get the right answer? There may be no perfect answer. It may be that we give the linear neuron a bunch of training cases with desired answers, and there's no set of weights that will give the desired answer. there's still some set of weights that gets the best approximation on all those training cases, minimises that error measure, summed over all training cases. And if we make the learning rate small enough, and we learn for long enough, we can get as close as we like to that best answer. Another question is, how quickly do we get towards the best answer? And even for a linear system, the learning can be quite slow, this kind of iterative learning. If two input dimensions are highly correlated, it's very hard to tell how much of the summed weight on both of those input dimensions should be attributed to each input dimension. So if, for example, we always get the same number of portions of ketchup and chips, we can't decide how much of the price is due to the ketchup and how much is due to the chips. And if they're almost always the same, it can take a long time for the learning to correctly attribute the price to the ketchup and the chips. There's an interesting relationship between the delta rule and the learning rule for perceptrons. So if you use the online version of the delta rule, where we change the weights after each training case, it's quite similar to the perceptron learning rule. In perceptron learning, we increment or decrement the weight vector by the input vector, but we only change the input vector when we make an error. In the online version of the delta rule, we increment or decrement the weight vector by the input vector, but we scale that by both the residual error and the learning rate. And one annoying thing about this is we have to choose a learning rate. If we choose a learning rate that's too big, the system will be unstable. And if we choose a learning rate that's too small, it'll take an unnecessarily long time to learn a sensible set of weights.